Okay, so now let's do this stuff. So first, exam 1. Okay, exam 1 is next Friday. So that must be the 9th. And the topics on that, let's just do everything up through strain and constitutive. Okay.
This includes strain. This test will include strain. This isn't just like do everything before that, right?
It includes strain and constitutive. That's right. So this just means I'm not going to put any principal stresses on it. And then I posted weekly assignment 1. And that is due Wednesday. What did I say the last one was? So it 7. That must be Valentine's Day. This is such a romantic weekly assignment. Any questions about the test or the weekly assignment? Okay, anybody have any homework questions you want me to talk about?
Yes.
Okay.
18B.
Okay.
Yeah. I didn't really get what C was asking. I had an idea and I went with it, but I'm not
Okay.
sure it's right.
Okay, gotcha. 18.
I think it would be the same deprivation, right? For C.
Whoops.
Because you haven't done it. So what in the X direction?
I'm excited to see what this problem is that caused so much chaos.
Okay, so you don't.
I don't remember this one.
Measurements for the X and Y axis, but it asks you to find the deform length of Z. But doesn't it say
Oh, okay.
I had a guess at a cube.
Yeah.
Does it say if it's a 1 centimeter cube? It is a cube. I also we know that. So we do know it's 1 centimeter. So it's asking to find the deform length without anything else with it. Yeah. So when you do cost ratio, then you can plug it back.
Yes, exactly.
So it would be the same deprivation as in the Y.
Okay, right. The key thing here is that if you have, well, let's see what it is. So you calculate Poisson's ratio. So this is, so 0.999.
Try not to scale.
Correct.
It's like 4 times as much.
Okay, so number 18.
Go, I guess.
So Poisson's ratio, okay, if you have a material and you're putting it in tension in the x direction, the strain in the two off-axis directions are going to be the same. You know, Poisson's ratio can be either negative EYY over EXX, or it's also equal to negative EZZ over EXX. Well, for that to be the same thing, you know that those two have to be the same. So then you can figure out the deformation from that, because so since you can calculate EYY, you can also calculate EZZ. And then the definition of EZZ is the deformed length minus the starting length divided by the starting length. So you can figure out the deformation or whatever you need.
Is there an easier way to remember which measurements to use for like YY and XX? Because I keep getting them mixed up. I think they also rotated their coordinate system. Yeah. Because then there's the Y is the moment of change.
Oh, okay, yes.
So it would be EXX.
You're right, yep.
EYY.
You're right, yep.
Which also is confusing at first.
Yeah.
So like what I'm confused on is for the EXS and EYY, should I use the measurements that are parallel or perpendicular to the axis that it's asking for? So like EYY, should I use the ones that follow the x-axis or?
So yeah, I mean, I guess use the coordinate system that's given there. So so if you're calculating the Poisson's ratio in this case, it's going to be negative EXX over EYY. Because what matters is just the loading axis. What's the loading axis? Or you could, now that I think about it, you could just scribble out that coordinate system and choose your own coordinate system. So why is it that those strains are the same? Come on. So why are the two off-axis strains the same?
Because the material is isomorphic. Isotropic.
Isotropic.
Isometric.
It's not isometric necessarily. Come on. But it comes from the fact that the Voigt strain is equal to a matrix like this, a compliance matrix. And we're multiplying this thing times a single this is a tensile test. So it looks like this. Okay, and so what that says is that EXX, if you just multiply out this matrix, is equal to sigma XX over E. EYY is equal to negative Poisson's ratio times sigma XX over E. And EZZ is negative Poisson's ratio sigma XX over E. So these are the same. that's only true for, being loaded along one axis only, like a tensile test. This is only for, uniaxial loading along the x-axis. Is that good enough for number 18? Or is there anything else you want to talk about? I think that's really the only thing that's different from other problems. So I'm just going to go on, I think. Any other homework questions you want me to talk about?
For part E there, how would you go like backwards to get the stress tensor?
Okay. Well, the easiest way to do it is you already, once you have,
Is that using the inverse compliance matrix?
yeah, so once you have the compliance matrix, just take that matrix to the -1 power, that's the inverse, and that'll give you the stiffness matrix. And then once you have the stiffness matrix, you can back calculate because you have those strain values.
Yeah, the void strain matrix.
Right. Because from that picture, you can write out the void strain and then just multiply it by the stiffness matrix and it'll give you the stress. So the void stress, then, this is the stiffness matrix, and the void stress is the stiffness matrix times the void strain.
And there are no shear strains?
I think it was all just, it was in uniaxial tension, right? So yes, no shear strains. Yeah. If after deformation the thing is like a rectangular solid, then there's no shears. Because the shears make it, change those angles. Okay, the one problem that we haven't done yet in strain and constitutive relationship, it's not like complicated or anything, but I haven't told you what you need to know about that. And this is just more information about what you do when you do a tensile test of a material. So let me talk about a tensile test to failure. And the picture I'm going to draw is pretty representative of metals overall. They'd have different values, but it would, qualitatively, the graph would look pretty similar. So you start out by applying a load to this thing, and, you measure the deformation. But if you keep increasing the load, you can plot out the stress versus the strain. And this is along the loading axis, so you can think of it like this. Okay. And zero stress corresponds to zero strain, so it starts out there. And then little by little you get part of a graph that looks like that. It's almost exactly aligned, okay? And so as you increase the stress, increase those tensile forces, it increases the stress, and that increases the strain in a linear way. And this is called the linear elastic region. And this is the region of deformation that this entire class is about. Elastic means that as long as you're in that region of this stress strain curve, if you let go of the forces, it returns to its original thing, okay?
So that's the only region that the compliance matrix works to convert.
Correct.
Stress and strain.
Yes, that's right. Do you know what elastic means?
Stretchy.
Yeah, so I mean, I think that's what most people say, and I think thinking about it that way maybe kind of made me misunderstand it for a while, because it's not exactly the stretchiness of it, it's the fact that it returns when you let go, you know?
So you have plastic and elastic, right?
Plastic is like a permanent deformation, yeah. So elastic means that when you let go of the forces, it goes back to its original shape. So like the elastic waistband on your underoos or whatever, you know, the thing that makes it elastic isn't that it stretches, because you could make it out of Play-Doh and they would stretch, but they wouldn't be very good as underpants, because when you let go, they would fall down, you know? So the elastic is the return to the original shape. Okay, so after this, two things happen pretty similarly. They don't always happen at exactly the same point, but now this graph switches over to two things. First, there's a nonlinear relationship between stress and strain. And also, deformations start to be permanent. So once you get to this nonlinear region, or right around this nonlinear region, if you let go, it won't go all the way back anymore. And then the graph does some funny things, sort of like that. At this point, right about here, it starts to matter how you calculate stress or strain. If you keep measuring the thickness of the material and measure the stress based on its actual thickness at that instant, this graph will actually look like this. This one is called the true strain and true stress. This is the one, this is what it would look like calculating the stress and strain the way we have before. Notice it doesn't make any difference until you get to this place where the cross-sectional area starts to decrease. This is called the engineering strain and stress. And this weird thing here, where it's like it starts to get weaker and then all of a sudden it gets stronger again, is called strain hardening. And I don't remember what causes that, but it's just something that you see in this tensile test. And the engineering strain versus the true strain starts to happen when the material starts necking, it's called. Necking begins, and that just means that when you stretch a material enough, it starts to do this. Okay, and then eventually that failure is going to happen in here at the thin region. And then this cutoff point is where it breaks. And if you're doing a tensile test on steel, it's a very loud thing. And if you're not expecting it, it's very startling. I know that from experience. And one thing, so based on this stress strain curve, the part that's circled is the only stuff we care about for our calculations in this class. Notice that the Young's modulus is the slope of this region, of that linear elastic region. What's the Young's modulus once you get out here to the nonlinear region? It's kind of a trick question because it doesn't matter. You're not going to use Young's modulus in calculations anymore at that point. Okay. Any questions about that? So one of the problems in strain and constitutive relationships is just kind of describing different regions here, you know. Okay, well, let's go back now. So that's the last stuff that is going to be on the exam. And now let's go back to principal stresses. Yeah.
You said the true strain was based on the area after that certain point. So what's the engineering strain based on?
The engineering strain is based on the original area. So you can imagine it's going to always be smaller because you're dividing by a bigger area. It's not taking into account that the cross-sectional area is changing.
So the actual measurement is going to be along the engineering strain closer or the true strain? Like if you're measuring, yeah.
They kind of, I mean, they just mean different things. I don't really know the answer to that, I guess. You use different ones in different applications, but you just have to know that there's a distinction between those and you have to know which one you're dealing with. Okay, so principal stresses. Okay, so practically speaking, how do you calculate the principal stresses? So if your stress tensor is, let me use the example I wrote down. So let's say that you have, oh, well, that's no good. So let's say you have 5, -2, 0, -2, 0, 0, 0, 0, -10. If you have a TI 89 or Inspire, bless you, then you're just going to write lowercase I v L of that matrix. And that's going to give you the 3 principal stresses. And if you do eigenvector, lowercase eig, capital VC of that matrix, it's going to give you the 3 principal axes in the same order. Okay. The principal axes aren't going to matter for us, but it's important to keep in mind that those tell you the orientation of that new principal coordinate system. Yeah?
What about TI-84?
TI-84 does not do it, and so you'll have to use something else. I'm not going to make you do it on tests, so all you need it for is for assignments. But you can use Wolfram Alpha, or you can find, just type in eigenvalue, eigenvector calculator, Google it, and you'll find software. Yep, so it's pretty easy. So let's do this. What does it say if you calculate this? So I'm going to go, so I'm going to make this matrix 5, -2, 0, -2, 0, 0, 0, 0, -10. And I'll call that matrix A. And then on the TI-89, I go to catalog, go to the E's. Run that for the matrix A, and it gives me so these principal stresses are -0.702, actually, there was one I didn't see here. So the first one it gives me is 5.70. Then the second one is -0.702, and the third one is 10, -10, I guess. And then for the eigenvectors, it gives me 0.944, negative 0.3310, 0.331, 0.9440, and then 001. And the form it gives me is a matrix, but these are the columns of the matrix. And when I say that it does them in the same order as the eigenvalues, it means that this eigenvector corresponds, the first eigenvector it gives me corresponds to the first eigenvalue, second, and third. Okay? So now based on this, there's 6 possible principal stress tensors that are just the different permutations of those 3 values along the main diagonal. So one could be this. One could be this. One could be this. And then we need 3 more.
You just put the signs.
The signs?
Yeah.
Where?
Like I'm saying for the other 3.
No, you can't flip the signs of the eigenvalues. You can flip the signs of the eigenvectors, but not the values. But you just need to come up with the different permutations, you know. So like 5.7, negative 10, negative 0.702. Negative 10, negative 0.702, 5.70. And then the last one, negative 0.702, 5.70, negative 10. Okay. So all of those are perfectly valid principal stress tensors. Okay, and if you drew the stress cubes for these, you would see that they, represent the same state of stress, just with different choices of what faces what. Okay. Now, the one thing, so starting with any one of these principal stress tensors, starting with any of these principal stress tensors, rotating the coordinate system 45 degrees about the middle principal stress axis gives a stress tensor with maximum absolute value of shear stress. I'm going to call that tau max. Okay, and tau max, most of the time we don't care about that stress tensor, we just care about the value. Well, the value is easier to calculate than rotating the coordinate system. This T max is just equal to the maximum principal stress minus the minimum principal stress divided by 2. So back to the example above. Let's say that the principal stress tensor I'm going to use is that first one. So 5.70, negative 0.702, negative 10. Sigma max is 5.70. Sigma min is negative 10. And so the maximum absolute value of shear stress is 5.70 minus negative 10 divided by 2. So 15.7 divided by 2, so 7.85. If we want to see that stress tensor, or one of many stress tensors that has this maximum shear, then we want to let me write it like this. The middle stress tensor is negative 0.702. Okay. And what position is that in? That's in the Y position. You see that? So we're going to rotate 45 degrees about Y. And so our rotation matrix is 0.7071, 0, negative 0.7071, 0, 1, 0, 0.7071, 0, 0.7071. And now our stress tensor with maximum shear is just going to be Q times that original, times that principal stress tensor, 5.70, negative 0.702, negative 10 times Q transpose. So let me do that. So, okay, so now I got those entered. So now I'm going to go Q times the principal stress tensor times Q transpose and the matrix I get is negative 2.15, 0, positive 7.85, 0, negative 0.702, 0, 7.85, 0, negative 2.15. And you can see those maximum shear stress here and here. They can come up in the matrix either positive or negative. Okay? Any questions about that? Okay, there are a few times that you'll have to come up with this tensor with that maximum shear stress in it by doing that 45-degree coordinate system transformation. But most of the time, all I want is just that maximum shear stress, so you can just use that formula. Okay, and the last thing I want to say today is there are times, probably at some point in passing in some class at the U or wherever you go, where a professor will say, use Moore's circle to calculate the principal stresses. That's a way that it used to be done graphically in the old days when calculating eigenvalues and eigenvectors was a major pain. You just tell them that Gaio said I should use eigenvalues instead because they make electronic digital calculators now. Okay, so remember that if and when this ever arises, this is like your permission slip. Actually, two people a long time ago that took this class from me, like actually came back to visit me because they were all excited. They're like, it just happened, this class. They said use Moore's circle. Or I think it was on an assignment actually. And they turned in their assignment but they went to go talk to their professor, and they had written that on their assignment. And they were like waiting for I think I had even said, like, let me know what they say when you tell them that. I want to hear their reaction. But it was pretty anticlimactic. They're just like, oh yeah, he said we should use calculators instead and do the eigenvalues. And the guy just sort of smiled and was like, yeah, that's fine.
What even is Moore's circle?
Oy, oy, oy.